We did KVL, KCL. Yep. So let's do KVL. What is KVL for this circuit? How many loops do we have? We have one loop, so we'll have one KVL equation. What is that one KVL equation? Vs is equal to Vr plus Vc plus Vl. Good job, Dylan. Okay, that's our one KVL equation. Here, we can draw on multiple nodes. I'll go ahead and make this node 1. This will be node 2. This will be node 3. This will be node 4. We can have a total of 4 KCL equations. Okay? What is the KCL equation at node 1? Okay, what about at 2? Okay, what about at 3? IC equals IL. And what about at 4? IL equals IS. So here, all of our currents are equal to each other. That's what KCL tells us. And all of our voltages sum to Vs. That's what our voltages tell us. Okay? The next step is we have to derive our constitutive equation. So step 1 is draw the circuit. Step 2, KVL, KCL, and then, oh, we forgot our component equations. What components do we have in this system? We have a resistor, a capacitor, and an inductor. Okay? What is the component equation for a resistor? It's Ohm's law. VR equals IR times R. Okay? What is the component equation for a capacitor? Okay, good job. What is the component equation for an inductor? There we go. These are all the equations that we need to solve the system. Okay, so that's step 2. Step 3 is now we have to derive our constitutive equation. Okay, these are the same steps as the RC system. So we have to pick one of these formulas to start out with. My suggestion, pick a formula that starts with a forcing function, which here is Vs. Okay? So which of these equations have Vs in them? It's the KVL equation. So we'll just start with a KVL equation. Okay? Now, it just conveniently has VR in it. Should we go ahead and solve for VR? Why not? We could solve the other ones in terms of VLR, though. Should we just go ahead and solve everything in terms of VR? Sure, why not? Okay, so we've got Vs is equal to VR plus, what equation can we use to get rid of Vc? Where do we see an equation that has VC in it? Yep, the component equation. So we can go ahead and plug VC is equal to 1 over C integral of IC dt. So this is 1 over C integral IC dt. And then VL, which is, where is an equation that we have that has VL in it? We got this one. So we can just plug in L DIL dt. Now hold on, wait a second. Where did that come from? We haven't had an integral in any of our equations before. We did something wrong. It is my fault. I did this on purpose. You can solve this because IC equals IR, IL equals IR. You can then plug in VR equals IRR, solve for VR. We're still going to have an integral and we're still going to have a derivative. It's gross because in order to do that you have to then integrate over the circuit, and it's just gross. Let's not do that. Let's not violate that one principle that I told you. We're looking for VR. We're not solving for VR right here. We'll figure out VR later. We're going to solve for either one of two variables. What are they? VC or IL. So not doing that, bad move. Instead, we're going to solve this for VC. So VS is equal to VR. What can we replace VR with? IRR. It's Pirate's favorite variables. We'll keep VC as is. And then what can we replace VL with? That one. L DIL dt. Okay? All right. So now what can we do with IR? It's this equation right here. So VS is equal to ICR plus VC plus L. What can we do with IL? Same thing. It's equal to IC. We know that because of this. We can also solve it just using these equations. They're all equal to each other. So dic dt. Okay. Now we have everything in terms of VC or IC. How do we get the IC in terms of VC? Where do we have an equation that uses IC? Yeah, we got this one right here. So if we just plug in that every time we see an IC, what we got is VS is equal to C dVC dt times R plus VC plus L d over dt of C dVC dt. Okay, that's gross. Let's go ahead and clean this up a little bit. I'm going to go ahead and move this one first, just so that we got, actually, no, I'm going to put that at the end. We'll take this one first because it has a double derivative. We'll take this one next because it has a single derivative, and we'll finish with VC. So I'm just going to rewrite this equation. Make it pretty. VS is equal to LC d squared VC over d squared dt squared plus CR dVc dt plus Vc. Okay, that's as pretty as I go, man. Although that's valid. Fair point. We now have this in terms of second order derivative, first order derivative, no derivative. Okay? This is as pretty as we can get it. This is only in terms of Vc and Vs. Here we have our forcing function. Here we have a function of Vc. We could have also solved for IL if you really wanted to. That wouldn't have been a problem. We would have gotten a very similar function to this. We would have been able to keep Vs. We would have had something that looks very much like this at the end. You'd have ended up with like something like Vs over R. But whatever. Okay. So this is our step 3. I'm going to go ahead and draw a box around this. Because that's kind of important. Step 4 in our 7-step process was we had to estimate a solution. Now, since this is a second order system, what that means is we have to take a function that is able to add to itself after 2 of its own derivatives. You don't have to cry, Jacob. I mean, we're not there yet, man. We're just getting started. Okay. Just like, can you hold it off to the end of class? Thank you. I mean, it's one thing if I know you're suffering, but it's another thing if, like, you're suffering in class. I just want to assume you go home and suffer, okay? Oh, man. I've already had too much sugar today. All right, so we have to guess a solution. Now, our solution is going to look, and this marker is dying. I'm gonna lift the cap off like a monster. This is not the right time to not have a dark marker. Okay, our solution is gonna look like this. Vc equals Vcc plus Vcp. We've seen that one before. But there is one difference. Vcc isn't the same. Our guess for Vcc has to include the fact that this is now a solution to a second order system. Because this is the solution to a second order system, we're going to take the assumption I used A1, didn't I? A1e to the S1t plus A2e to the S2t. Somebody left the lid off this marker! Must be the freshman, like a disease. I'll have to let them know when I have them in class later. Hi, I'm teaching you. You're all a disease. Boy, I really shouldn't be posting this on YouTube. Yep. Disclaimer. I actually meant that. Okay, so VCP is going to be the same. Because we're dealing with a constant voltage source, we're going to have an A3 that is just A3. Hey! Awesome. Okay, so that little bit different already. Now we're going to go to step 5, which is solving for S. Okay? So in step 5, when we go to solve for S, what we do is we take the homogeneous equation and we plug in VCC. Because remember, the goal of the complementary solution is the solution plus its derivative has to equal 0. Because we want that one to go away. Okay? So we'll take this, plug it into the homogeneous equation, and then go with it. So what is the homogeneous equation? Well, that's the complementary solution. What's the homogeneous equation? You have impeccable control of your eyebrows, sir. That was amazing. What is the homogeneous equation? What? Does anybody have a guess? It's not VCC. It's not any of these. It's if we take this one, but we take out Vs. So if you put this equal to 0, then there's no forcing function, and this is the homogeneous equation minus Vs. Okay? So the homogeneous equation that we write is 0 is equal to LC d squared Vc over dt squared plus CR dVc dt plus Vc. Okay? The only thing that differs between this equation and our constitutive equation is that we don't have a Vs. And the reason for that is because since this is the complementary solution, this is the solution that goes away, which means it is not dependent on the forcing function. The forcing function does its own thing. This is dependent on the behavior of the system, the components that are included in this system. Here we got an R, a C, and an L. All of those components come to play. We have an R, a C, and an L in our homogeneous equation. Okay, now all we're going to do is we're going to plug in VCC in for VC. Because that's what you do with a homogeneous equation. You solve for the part that goes away. So you have 0 is equal to LC d squared VCC dt squared plus CR dVCC dt plus VCC. This is about to get real gross, fam. Huh? So, it's because somebody a long time ago loved you. And it's because they loved you, they created this really disgusting math. Like, here, it's math vomit. Just for you, Sal. Okay. There's a lot of C's in there. Hey, that's a good thing.
I guess C's get the grades, huh?
Touche, my friend. You should not have had pie.
I did.
You should have had pie. Maybe you'd be in like a sugar coma or something and you just brought your A game of jokes today. It's good. Please don't tell me you have better ones. Okay, now what we're going to do is we're going to plug in what we know for VCC into VCC. Okay? So here, LC d squared over dt squared of A1e to the S1t plus A2e to the S2t plus CR times the derivative of A1e to the S1t plus A2e to the S2t plus A1e to the S1t plus, that's a 2, a 2e to the s2t. Wow, I managed to keep that all on the screen. It's amazing. Well, that's fun. All right, let's take them derivatives. So, this equation gets bigger. 0 is equal to LC d squared, nope, I'm going to take the derivative. So LC times S1 squared A1 e to the S1t plus S2 squared A2 e to the S2t. That's this double derivative. You just pull out an S1 every time you take a derivative. You pull out an S2 every time you take a derivative. Okay? Plus CR times S1 A1 e to the S1t plus S2 A2 e to the S2t plus A1 e to the S1t plus A2 e to the S2t. I'm going to go ahead and give you a spoiler alert. Most of the time you don't use this to solve your problems. There's an easier way. Because we're engineers and we hate friggin' doing math, okay? I mean, we need to do it when we need to do it, but this is, yikes. I'm only doing this for illustration purposes. Which is what your teachers tell you when they're deriving stuff, right? Okay, I'm going to go ahead and say this. Can I add a function of some constants and multiply it by e to the s1t plus some function of constants multiplied by e to the s2t and have them equal 0? These are two different time functions. In order for this to be true, the following must be true. There is absolutely no way that we can add two exponential functions multiplied by some constant, because that's really what all this comes down to. A2, A1, S2, S1, all of those are constants. They don't change with time. They're not time variant. And because of that, what we end up with here is the only way this can be true is if either A, S1 equals S2, which creates a singularity in our solution method. We're not going to talk about that yet. Or F1 and F2, both which are functions of constants, which are just A2 and A1, S1, S2, multiplies all of these things added together. Those have to be equal to 0. We're going to go ahead and go under this assumption, just because, again, if S1 equals S2, it creates a weird singularity. So long as S1 does not equal S2, we can solve this function by knowing that now we have two independent time functions. We have two different transfer functions occurring simultaneously. One of those transfer functions is caused by the presence of the inductor. One of those time functions is caused by the presence of the capacitor. Both of them have to simultaneously be true. Both of them have to be transient. So we now solve the problem with these assumptions where we break this up, where every time we have an S1 e to the S1t or whatever, this plus this plus this has to equal 0. This plus this plus this has to equal 0. We have to have that because there is no way for all times t to have two different exponential functions add to 0. It's impossible. It's like trying to take x plus x squared. You just multiply each of them by a constant. You know, there is no way to solve this function a1 x plus a2 x squared is equal to 0. You can find in exactly one point where this is true. But for all times t, this is not true. X equals 2, the whole thing blows up. X equals 3, the whole thing blows up. At x equals 0, this is true no matter what. But not at x equals 1. Unless a1 is equal to 0 and a2 is equal to 0. If a1 and a2 are equal to 0, this is always 0 for all times t, for all values of x. Okay? And that's basically what we're doing here. We know that everything that has an x in it, which here this is our e to the s1t, that all of the constants in front of that have to add to 0. Similarly, every constant that's in front of the e to the s2t has to add to 0. I told you things were going to hit the fan. Yep. Feces are there. They are spread across the room. I ran out of whiteboard. I want to. I want to make Gabby move. It's her birthday. No, I'm just going to erase. I'm good. I'll keep the equations up that we need. We don't need these anymore. I'm going to go ahead and rewrite this up here. So our constitutive equation is Vs equals LC d squared Vc dt squared plus Cr dVc dt plus Vc. Okay, and then we've got our estimate, which is Vc is equal to Vcc plus Vcp. Vcc is equal to a1 e to the s1t plus a2 e to the s2t, and Vcp is equal to a3. That's all the equations we need for now. Oh, I'm not going to erase this equation yet because I kind of need that one. This is just much more impressive when I write across all of the boards. Oh well. Okay, so we have that equation. We're now going to break it up, and I'm going to pull out every component that has an e to the s1t and every component that has an e to the s2t. I'm going to break them into two different functions. So function 1 is e to the s1t, okay? Everything that I have that has an e to the s1t, I'm going to put it here. So I've got 0 is equal to LC s1 squared a1 e to the s1t plus CR s1 a1 e to the s1t plus a1 e to the s1t. That is half of the equation. Nice. every one of these components has a1e to the s1t in it. When we broke this equation up into two, we now have the ability to divide both sides by a1e to the s1t. So we do that. If you divide both sides by a1e to the s1t, what you get is 0 is equal to LC s1 squared plus CR s1 plus 1. Finally, a nicer looking equation. Don't get used to it. What is the solution to this? How do we solve the solution to this? We know what L, C, and R are. We know what 1 is. I counted to it last night. It's my nighttime activities. I spent an hour trying to count to 1. Point 0.00000002. 0.00000003. Yep. This is why I'm so slow in grading all of your papers. I need to find better hobbies. How do we solve this? We do not know what S1 is. We're solving for S1. Here we have a squared, a single, we have a 1. The only way you're going to be able to solve this, you're thinking of it, it's the quadratic equation. So, quadratic equation is S1 is equal to negative B, which is here, that's CR. Yep, negative B plus or minus 2. No. Nope. Nope. Negative B plus or minus the square root of B squared minus 4AC divided by 2A. Okay? We plug in what each of these mean. FYI, you'll notice, oh yeah, never mind, I'll get there. So here we have two different values for S1. That's fun. So we'll say S1 is equal to negative CR plus or minus the square root of C squared R squared minus 4 LC times 1 divided by 2 LC. Also fun. Great times. It's good enjoyment. So, rousing session of math. I did this with all of my boating buddies in boating club. We would just go out on a boat and solve derivatives. Yeah, I don't remember the last time I've been on a boat. I think I saw a boat when I was 3. What? I was on a boat when I went to St. Louis. There was like a food boat. I was 10. That was the last time I was on a boat. Boy, I'm deprived. No, because the boat was completely enclosed. I was 10. And I got seasick on the boat. Yep. It wasn't even moving. It was just sitting in the Missouri River right next to St. Louis. And I'm sitting there trying to eat, and I'm like, I'm about to throw up. That was the last time I was on a boat. That's why I'm deprived. Okay. So this is the ultimate solution to S1. Okay? I am going to clean this up in a little bit. If we solve this exact equation for S2, guess what we get? We get this again. because it's the same exact equation. Now, that just means to me that we're just going to say S1 is not equal to S2. Therefore, S1 is equal to negative CR plus square root C squared R squared minus 4LC divided by 2LC. Okay, and then we'll make S2 be equal to negative CR minus the square root of C squared R squared minus 4LC divided by 2LC. Okay, man, this is gross. We're going to break this up into a couple of different terms. Okay, this rewritten now looks like this. S1 is equal to negative R over L, 2L, sorry, plus, oh, I guess that's S2, dang it, doesn't matter. Switching the signs on you. Okay, plus the square root, oh, sorry, RC square root of 1 minus four LC divided by 2LC. If we go ahead and simplify that a little bit more, we get S1 is equal to negative R over 2L plus what, R over 2L times the square root of 1 minus 4 LC. Okay, so it's not really all that pretty, but it's slightly prettier. Now what you'll notice here is we have two distinct terms. It is possible to make S1 equals S2 if, oh, sorry, I didn't write out S2. S2 is just equal to negative R over 2L minus R over 2L square root of 1 minus 4 LC. How can we make S1 equal to S2? What would have to be true in order for S1 to equal S2? This is kind of a side note, has nothing to do with the solution.
Does the resistance have to be 0?
That would do it, yeah. But there's another thing that doesn't involve making the resistance equal to 0. But yes, you are right. Because this is the same first term, plus and minus the same last term, the only way these can be equal is if this last term is equal to 0. So as Ben said, if you just make R equal to 0, done. But we're not going to do that because we're looking at an RLC circuit. Yes, okay, if you plug in R equals 0, what ends up happening is you have a harmonic system. Without having a resistance in here, any amount of power that is added to the system oscillates between the capacitor and the inductor. And you end up having a sine wave resultant, where this is constantly charging the capacitor while discharging the inductor, and then turns around and charges the capacitor, charges the inductor while discharging the capacitor. Okay, it becomes a harmonic system. I wasn't going to talk about that yet. LC circuits are actually very dangerous, but that's different. S1 equals S2 if the square root of 1 minus 4 LC is equal to 0. So if 1 minus 4 LC is equal to 0, then these two become equal to each other. That's it. That's all it takes. Okay? What happens if 1 minus 4LC is less than 0? What does that do to our equation? If it's less than 0, it means it's a negative number. What happens when you have a square root of a negative number? It becomes imaginary. This is where things get gross. Okay? So if that's negative, this is imaginary. If it's positive, this is real. There's a distinction. Boy, I hope I picked the parameters necessary to make this positive. I'm never very good at picking numbers for these problems.
You just make a lot.
Yeah, as I go. I'm solving all of this out of my head. Yep. Okay, so that's just a weird side note. We've now solved for S. We know what S is. We've done step 5. Now it's time for step 6, which is solving for the particular solution. To solve for the particular solution, we use the non-homogeneous equation. What is the non-homogeneous equation for this system? What is the non-homogeneous equation? What was the homogeneous equation? It's the constitutive equation. For the homogeneous one, you make Vs equals 0. For the non-homogeneous one, which is how you solve for the long-term behavior of the system, you keep Vs in. It's just equal to the constitutive equation. Okay? So, for the non-homogeneous equation, I just write out my constitutive equation as is. LC d squared Vc over dt squared plus Cr dVc dt plus Vc. Now, since this is the non-homogeneous equation, and since we're solving for the particular solution, we're going to go ahead and plug in the particular solution, VCP. Now, this one's going to be a lot prettier, I promise. LC d squared VCP over dt squared plus Cr dVcP dt plus VCP. What is VCP? It's just A3. So here, I can plug in A3 every time I see VCP. Vs is equal to LC d squared over dt squared of A3 plus Cr d over dt of A3 plus A3. What's the next step?
Simplify the derivative part.
How do we simplify the derivatives? What is the derivative of A3? It's a big 0, because that's a constant. Those two go away. What we end up with is Vs is equal to A3. Shocker. In the long-term solution for this problem, Vc is equal to Vs. That's good. It's a good sign. Some good feels right there. Loving it. Okay, so now we've solved 6. Now we only have one step left. 7. We got to figure out what A1 and A2 are. And we do that by putting in our initial conditions. So step 7 is your initial conditions step. Okay? What are our initial conditions? What does initial condition mean? Time equals 0 at some time value. We have to know what certain values are so that we can figure out what the system looks like. As it is, this solution as is with different A1 and A2 values can solve for any system, really. And just plug in a different A1, different A2. It's got to have the same time function because it's got to have S1, S2 according to what we said. But without knowing our initial conditions, we don't know, is the system already at steady state? Because if that's the case, then A1, A2 are equal to 0. Is the system really far away from steady state? In that case, A1 and A2 are going to be very large. What are our initial conditions? I gave you 2. That's a bad sign. Now, the reason why that's a bad sign is because we're going to have to use both of them. And if you notice, only one of those initial conditions has a VC in it. So we know, if we just go back and plug in our value for VC, VC is equal to VCC plus VCP. If we plug in what we know for VCC and VCP, we get VC is equal to A1 e to the S1t plus A2 e to the S2t, and then VCP is A3, which we know A3 is equal to VS. If we plug in our initial condition, we know at t equals 0, VC is equal to 0. We're solving for VC, so that's nice. So we get 0 is equal to A1 e to the S1 times 0 plus A2 e to the S2 times 0 plus VS. What is e to the 0? It's 1. So this simplifies down to 0 equals A1 plus A2 plus VS. Also known as negative VS is equal to A1 plus A2. We didn't solve for either of them. That's why I gave you 2 initial conditions. Hate. Loathe entirely. Okay, so I have a eraser right here. Nice. I want to bend down. It's too far. Okay, so I solved for one of the 2 initial conditions. This is one of the 2 equations we're going to have to use to solve for A1 and A2. Man, this problem is long. We're almost done. I'm lying to you. We're going to keep going for hours. For days. For days. Okay, the other initial condition is IL is equal to 0. How do we use that? We don't have a function for IL. What's that? It equals 0 at 0. Yes, but we don't know where IL equals anywhere else. And how do we use this to solve for A1 and A2? How do we solve for the function IL so that we can set it equal to 0? Well, I erased all of our KVL, KCL equations. I did. And one of the things that you can do with the KVL and KCL equations are you can solve for IL is equal to some function of VC. Okay? I'm going to go ahead and do that quick. From this equation, we know from KCL, we know IL is equal to IC. Okay? That should be up at the top of your page. Since IL equals IC, we know IC is equal to C dVC dt. Which means IL is equal to C dVC dt. Now we solved for VC. If we take the derivative of VC with time, we multiply it by C, we'll get IL. Let's do it. So, I'm going to go ahead and plug in what we just wrote for dVC. So it's IL equals C d dt of A1 e to the S1t plus A2 e to the S2t plus A3. Because that's what we got for VC. We know what A3 is. We know what S1 is. We know what S2 is. We've already solved for all of these monsters. If we take this derivative, we get IL is equal to C times S1 A1 e to the S1t plus S2 A2 e to the S2t plus 0. That's probably the most enthusiastic right parentheses I've ever drawn. I'm so proud of me. My mom's gonna be happy. I'm gonna show her this YouTube video later. It's for you, Mom. That was in this video. Yeah. But in fairness, I mean, who doesn't know that? It's freshmen. But then they graduate out of being freshmen and they're like, ugh, freshmen are a disease. Yep, it's not twice in the same video. I will not be showing this to my mom. This is gonna come back and bite me someday. Okay, so, yeah, but they left the caps off of the markers. They deserved it.
I'm not disagreeing, I'm just saying it's on YouTube.
I know. I hope YouTube is as empathetic to whiteboard markers as I am. That love in my heart. Huh?
Maybe an age restriction on YouTube.
Yep. Sorry, you're under 18. You cannot watch my videos. I don't care if you're in my class. Okay. So now we have this. And we can solve this because we know what the initial condition is. At t equals 0, IL equals 0. So we plug in t equals 0, and IL equals 0, and what we end up with is 0 is equal to CS1 A1 e to the S1 times 0 plus CS2 A2 e to the S2 times 0. As we've already pointed out, e to the 0 is equal to 1, which means this simplifies down to 0 is equal to C S1 A1 plus C S2 A2. You can divide out C, and what you end up with is A1 is equal to negative S2 over S1 A2. And now we can plug that into this and solve for our final system. Okay? And once we've solved for our final system, are we done? Gabby knows the truth. I threw in that extra little end curveball. What are we trying to solve for in this problem? VR. When did we solve for VR? Never. We never solve for VR. You had to do it twice. One just did not sufficiently express the frustration. Now that said, it's actually not that far. We've already halfway solved for VR. Because when we solve for IL equals IR. Nope. We've already got this equation right here, and we know it equals to IR. Now here, at this point, we know what S1 is, we know what A1 is, we know what S1 is, we know what AS2 is, we know what A2 is. We have everything. Because we just solved for A1, you can plug it into here, get A2. We have everything. All we need to do is just multiply it by R. That's it. And then we're done. So there we go. We take this equation here, which we know equals 0 at 0, which we also know equals 0 at t equals infinity, because both S1 and S2 go away. They're transient solutions. So we have no current going through the resistor immediately after flipping the switch. Then what happens is current slowly travels through the resistor, increasing to a point where it then stops, turns around, and begins decreasing again, and goes back to 0. At the start, the voltage across the resistor is equal to 0. At the end, the voltage across the resistor is equal to 0. At some point in between, there has to be a current traveling through the circuit that travels through this resistor and loads this capacitor. As soon as the capacitor is fully loaded, then the resistor current drops off. So if we were to plot VR with time, it would look like this. That's awesome. You're pretty stupid, VR. Dang it. Oh man, I'm using those offensive words again. YouTube moderating. And feel bad for anybody watching this video. Even without calling freshmen a disease, they'd probably want to moderate me. Like, you're teaching that hard math. Gross. Okay. Now, I'm also going to plot out VC and VL. Just because I can. So look at this equation. VC looks like this. VL looks like this. If you add all three of these together, they equal a straight line. Because they equal Vs. Because KVL is still true. All right, let's take a 10-minute break. I will see you back here at 10:10. And we will talk about how to turn this into a much simpler problem.